Okay, so in this last part, I want to illustrate how you go about integrating more complicated functions, let's say, when you want to figure out these series that I was talking about. So let's say, let's say we have basically as a goal to find the even series, Legendre series for x. So basically your function now is x. Or maybe later on, maybe you want to integrate a higher power of x, let's say x squared and so on. Well, by hand, it's going to be really tedious, but the point I'm trying to make here is that you could use these relations repeatedly until you write everything in terms of basic Legendre polynomials evaluated at 0. So the interval is 0, 1. And let's start with the formula for the coefficient a to n. Right, so if I want the even series, this will be for n plus 1, the integral from 0 to 1, x p to n of x dx. All right, so notice that I'm going to have to start with this now and replace xp to n with whatever I see here, but again, n will be replaced by 2n because that's my index here. So 4n plus 1, and now replace n with 2n. So I'm going to have inside the integral 2n plus 1, 4n plus 1, because I replace n with 2n, p 2n plus 1 of x, plus 2n 4n plus 1, p 2n minus 1 of x, inside the integral. And notice already, we know that the case n equals 0 is separately, is to be treated separately, because when n is 0, 2n minus 1 is minus 1, and that's not defined. And now comes the tedious part. Each of these, you can split the integral into two terms, right? So you have this times this becomes 2n plus 1, the integral from 0 to 1, p to n plus 1 of x. And this times this is 2n, the integral from 0 to 1, p to n minus 1 of x dx. And now for each of these, I'll have to integrate using this formula. And again, you'll have to do those substitutions very carefully, and you can do them on a scratch paper if you feel like it's easier. So to get p to n plus 1 of x, I'll replace n with 2n plus 1 everywhere here. So I'm going to have 1 over, that becomes 4n plus 3, and in parentheses p prime to n plus 2 of x minus p prime to n of x. And then plus 2n. And now I go back to this formula and I replace n with 2n minus 1. So again, do it on scratch paper if you want to. That's going to be, for example, here when I replace n with 2n minus 1, I'll have basically 2 quantity 2n minus 1 plus 1. That makes it 4n minus 1. Okay, so 2n, the integral from 0 to 1, 1 over 4n minus 1, and then in the parentheses p prime, n was 2n minus 1, so that becomes, let's see, 2n. And then p prime, 2n minus 2. Again, the case n equals 0 is separately treated. Okay, so with a little practice now we can basically integrate right away. So 2n plus 1 over 4n plus 3. The integral is going to be p2n plus 2 minus p2n between 0 and 1. So again, it'll be 1 minus 1 when you plug in 1 minus p2n plus 2 of 0 minus p2n of 0. The second integral will be 2n over 4n minus 1. Once again, plug in 1 into the antiderivative. That's 1 minus 1. And then plug in 0. That's p2n of 0 minus p2n minus 2 of 0. And like I said, we will be perfectly happy to leave the answer like that. So for instance, you could leave it like 2n plus 1 over 4n plus 3. Just clean up this a little bit. So that's p2n of 0 minus p2n plus 2 of 0. 2n over 4n minus 1, p2n minus 2 of 0 minus p2n of 0. Oops, that's out of range again. Sorry about that. So, like I said, we can leave it as is. So when we get to the answer in terms of these even polynomials at 0, you could leave the answer like that unless I say otherwise, but I won't. I will maybe ask you to do that just for one instance, maybe as an extra question, write down what, let's say, p2n plus 2 of 0 is. But we're not going to do it for all of them because that will make the problem far longer than it's worth it. So let's leave it at that for now. And when we continue next time, so the goal for the next lecture is to do a boundary value problem from top to finish. One reminder before we do that, remember in the spherical coordinates, the connection between the Sturmoville problem we get and the Legendre equation is via this substitution, x equals cosine of theta. So remember that the Sturmoville problem that we ended up with was actually sine of theta, h prime of theta prime, plus lambda sine of theta, h of theta equals 0. And only via a certain substitution, only via this substitution, x equals cosine of theta, we arrive to the Legendre equation, which is 1 minus x squared y prime plus lambda y equals 0. So basically, when the time comes to actually solve the Sturm-Liouville problem, the solutions or the eigenfunction will be not Pn of x, but Pn of cosine of theta. You will replace back x with cosine of theta. So the eigenfunctions will be Pn of cosine of theta, and the Legendre series will be in terms of Pn of cosine of theta. We'll get to that part. Basically, all of these formulas can be written in terms of cosine of theta. So just like the Legendre polynomials were orthogonal via with wave function 1, right? So when you have this integral equal to 0 if m is not equal to n, and 2 over 2n plus 1 if n is equal to n. The same thing can be rewritten via the substitution as the integral from 0 to pi, Pn of cosine of theta, Pm of cosine of theta, sine of theta, d theta. So in other words, you will say that Pn of cosine of theta are orthogonal on 0 pi with weight function sine of theta. So actually the formula sheet gives you the Legendre series in terms of this cosine of theta. But I want to point out that even if you don't have these separated formulas, when the time comes to actually come up with a serious format for your solution in spherical coordinates, you're going to end up basically with something like this. And via this substitution, that brings you to the Legendre polynomials that we talked about so far. But we'll deal with that on the next lecture. So that's it for today.